Uh, I would like to invite Professor Tripathi for the next talk. Professor Tripathi is a higher administrative grade professor of civil engineering at IIT Kanpur. He is the recipient of Swanti Soren Bhatnagar Award and J.C. Bose National Fellowship. He received his BTech from IIT BHU and PhD from Leiden University, UK. His research interests include aerosol science and technology, low-cost sensor for air quality monitoring, air pollution source identification in near real time, and aerosol land use rainfall climate coupling, large-scale chamber aerosol experiment for air safety. And as we know very well Professor Tripathi, and I think throughout India, everybody knows about his work on clean air. So over to you, Professor Tripathi.
Thank you. So I'm mostly going to talk about some of the work which is happening as a part of this National Clean Air Program, which is the first comprehensive program, nationwide program to deal with the problem of air pollution, and what some of our group and other institutions are doing to combat this menace in the country. So talk is organized around National Clean Air Program and how we are trying to increase the footprint of air quality monitoring in the country by developing low-cost, affordable solutions, and then a very exciting new project we are doing to monitor air quality across the rural areas in the states of Uttar Pradesh and Bihar. So you know that Government of India launched this very major program, National Clean Air Program, with a goal to cut down particulate matter 2.5 by 30 to 40% in next 2 years, which they have revised to make it more ambitious, basically to increase it to 40% by 2026. And while doing so, they want to abate, prevent, and plug different kind of pollution sources by different ways and means, which are shown here, that they want to increase data. It has to be data-centric, data-driven, based on the science, sound science foundation. They want to implement policies. New institutions are planned to be created. As you see, this new commission to deal with their quality of Delhi NCR is part of that. And they also want to mitigate across the sectors different kind of sources. That's what is listed on the bottom, somewhat that was also talked by the Commissioner Dr. Rajasekhar. So our idea of this monitoring or sound, robust air quality management is mostly what you see in this cartoon, that you start with generating more science, more data. Then based on that, you develop new technologies which are suitable for our country. You create capacity at local and state levels, and you try to run this circle. And in the heart of that, we are going to discuss sensor-based solution which are indigenous in nature. So if you look, there are two maps of India shown here in this slide. On the left is the current state of monitoring, which basically shows there are about 350 to 400 continuous monitoring stations operational in the country, and around same, for a little more, are manual monitoring stations. So altogether about 700-800. And a very modest projected need on the right-hand side map is about 4,000 monitors. So the gap is very large, it's about few thousands, and each of them cost you about 1.5 crore. So if you were to meet this gap currently, for a very modest expectation, one is going to invest about 6,000 crores, and that is all imported monitor. And that is one thing what I'm going to discuss here, what kind of new technologies, new approaches we are trying here so that we can meet this need without having to incur so much money on import. Second thing, I'm going to discuss more or focus more on particulate matter 2.5, which is the primary health hazard. As of now, it is estimated that 2 million deaths are happening in India every year because of PM 2.5. And it's not only impacting us. Now there are very clear sound research that they are also entering into the fetus of the mother's womb. So these black carbon particles are actually entering into the cells of this newborn baby, which is very, very dangerous thing. So therefore, we need to monitor this in a better way to have more effective management. So one structure or framework which we proposed some time back was where you go from global to regional to the local scale monitoring by using either global models projections or regional network, which is in the center of this plot, to a combination of sensor combined with mobile based laboratory. Our laboratory where you can take anywhere and you can plug in and you can start sampling with that laboratory. And in that direction, some of the next few slides I'm going to talk about that where we have tried to improve precision and accuracy of these sensors. So if you look at the cost difference, one sensor costs about 1/20th of a government monitor if you only think about particulate matter 2.5. Current conventional monitors which government uses cost you about 20 lakh and one sensor costs you about 1 lakh. And if you add all these sensors together for particulate matter and gases, it costs you 3 to 4 lakh, and the current monitoring stations are 1.5 crore. So you can save money of about 20 to 50x, and all that money will stay within the country. So how have we looked into the accuracy of these sensors? We have placed these sensors next to these very accurate monitors which government uses, and that is what you see here on the x-axis are the measurements from BAM, that is a beta attenuation monitor, and the y-axis you have sensors data, and you see there is very interesting linear trend that emerges by looking at the intercomparison of these two different kind of monitoring techniques, and that is very easily implementable. So in fact, this particular work and its outcome is already being used by US Environment Protection Agency. Next, we looked into the similar issue of gas sensors. So what you see that there are 5 to 6 important criteria pollutants which generally government monitors. These are particulate matter and a number of gaseous pollutants. Here what you see are the similar results shown for two different kind of gas sensors, NOx and ozone. And what you see by looking at these violin plots, that by making use of several machine learning technologies, you could improve the accuracy of NOx and ozone, these two very, very important pollutants which are dangerous for human health, can be significantly improved, and error can be brought down. If you look at the last violin plot, error can be brought down to about 10%. So what you see, by now what we have seen that particulate matter and two important gases, you can measure by these sensors within an accuracy of 10 to 15%, and these are very scalable. Now, remember what I said before, that these results were obtained by co-locating these sensors next to government monitors. But when you are going to scale these monitoring network, like in the city of Lucknow, I am going to show you some results, it is not easy or feasible to have a co-location of each and every sensors. And therefore, we tried to have these sensors deployed across the city of Mumbai, where Maharashtra Pollution Control Board collaborated with us and gave us access to all their monitoring stations, which were 15 in numbers, and we spread out about 40 indigenously integrated these sensing units. And here I just show you the results from two different locations, one at the airport and another at Ville-Parle. And both plots show you three lines. One is the measurement made by the sensor, second is measurement by the government monitoring unit, and third is where by obtaining a correction factor between these two measurements, and then that correction was applied to the sensor data. And what you see the corrected measurements are very accurately following that measured by the government monitor. And that was the result we obtained across entire Mumbai city for about 7 months. So all that what we learned from our laboratory co-location, now what you see worked very well over the scale of Mumbai city. And next, what we did now is that when you do not have sufficient co-location data, because the technology has to come to a level where very limited co-located data is available, and you try to harness the power of machine learning and artificial intelligence, and then make the sensor learn what is being measured by the government monitor. So this is a work we did with our electrical engineering colleagues who are very strong in machine learning, Vipul Arora's team, where on the left what you see, at several locations in Mumbai we had sufficient co-located data, and we call them the receptor site, and then made the model learn, a meta-learning approach we applied, which is kind of a model which is always learning to learn. And that was applied to a target site, and we again had some very, very interesting results. So this is all about the effort what we have put in to increase the accuracy and precision of these sensors data. Now, another problem we are working with one of the colleague in civil engineering, Hemant Gahlaut, who is an expert on optimization. This is a problem of how to choose the location of sensors. If you have only few monitors, for example, in Kanpur city, we are running now 3 or 4 monitors. So for a size of Kanpur city, putting 3 or 4 monitor is not difficult. You can make a qualitative judgment. But when you are going to put 100 sensors in Kanpur, you need to have a better mathematical framework where you choose the sites in a way so that the outcome can be maximized. And that is what we have tried to do here. We have tried to make use of a very neat optimization algorithm which relies on some of very high resolution data which was available for the city of Surat. As I talk, this work is implemented in Surat city. This is a map of Surat where we had very high resolution population density and source information was available. By combining this into a single optimization problem, we could predict that depending on how much resources you have at your hand, whether 20 sensor or 25 sensors or 15 or 5, you can choose these locations. Your algorithm will decide where are you going to put this sensor so that you can get maximum outcome what is expected from these. This is another example. These are different examples of this emerging technology where currently we are running a network of about 75 sensors in Lucknow, which is what you see on the right is map of Lucknow city, and all these circles show you the locations of sensors. And we are able to get very accurate information about the hotspot, which is basically the locations where generally we sample very high amount of particulate matter or pollution. We tried to apply several kind of statistical technique, and consistently each one of them gave us same locations which generally shows much higher amount of particulate matter, which is shown by these pink circles on this map. So what you see here, that these are the locations which the city officials would definitely like to do something about so that the people's exposure can be minimized. Another interesting application of this technology, what we are currently trying, is to make use of this micro-satellite imagery, which is available at every locations over this planet once or twice a day. And we are making use of some artificial intelligence technique, which are, this work is in collaboration with some of the colleagues of computer science like Professor Piyush Rai's team, and they are applying sequentially a couple of artificial intelligence models so that you can increase the footprint of monitoring further, what you have seen by combining the government monitoring network as well as the sensors network. So I don't want to go into the detail of that. This is just an example that currently in Chennai, we are running a network of about 40 sensors. There is another network which is running in Guwahati of another 40 sensors. We are also trying to make use of the technology to predict in a very cost-effective way, efficient manner, the kind of sources which are responsible for this pollution. And we had reasonable amount of success here. What you see on the left, there are two pies, on the right there are two pies. They are same prediction of the source contribution to a particular site or two sites in Delhi, and what you see the modeled, the one which is modeled by a combination of machine learning models and one which is based on measurements, they agree reasonably well, and particularly for traffic related pollutions. And these kind of technologies can help us scale these source attribution techniques across the country as we move away from towns and cities to the rural areas. So currently in this map, what you see that in collaborative approach, different cities, states, where slowly our network is proliferating. As I said that several cities on east, west flank of India, already we have sensors network operational. And in the state of Uttar Pradesh and Bihar, we are putting two very dense network of sensors. This is what already we have an agreement. This is approved under a program of Office of Principal Scientific Advisor. In Bihar, we are going to put sensors in 550 blocks. So that will cover basically entire Bihar, and we have entered into a collaboration with Bihar government and with the Uttar Pradesh government. It has gone at an advanced stage, and hopefully soon we'll have approval from them and a lot of new information that is going to come once these networks are operational. I'm not going to go into the detail of that, and this is going to be my final slide. This is another work which we have been doing for some time to have a very accurate idea at mechanistic level about the adverse health impact of these particulate matter. So through chemical assays, you can get something what is called as oxidative potential, and that gives you very accurate information about how particulate matter is impacting the lung cells, the cells which are sitting in your lung. And therefore, higher is the oxidative potential, higher damage these particulate matter can do to your lung. So there are two kind of work we have done over Delhi where we were able to map the oxidative potential to the chemical speciation of particulate matter and furthermore to the sources. And these kind of technique we are hoping also to scale on the backbone of the networks which are going to be operational in the states of Uttar Pradesh and Bihar. And the information that is going to give us will be extremely useful for the policymakers or the models, something like what C-STEP is running, Safari kind of model, to give policymakers another lever when they are concerned about the economic cost and benefit. I think health cost and benefit analysis may also be very useful to understand, mitigate, and plug these sources. Okay, thank you.
Okay, please go ahead.
I have a question for Prof. Tripathi first. What is the life of these sensors that you plan to, that you have sort of put in various places?
1 year. Yeah, the unit can last for 5 years, but the sensor needs to be replaced every year, which costs a few thousand rupees. The sensor is a part of a small unit.
Rupees, or you can have it. What is the, the scientific difference between the technology of these things? And second thing, you said that it's about the expenditure 1.5 crores for each monitoring station. That is the estimate. To me, it sounds like it should be much less than that.
No, it's not. Actually, the government monitoring station costs 1.3 to 1.1 crore is the installation capital cost, and 40 lakh is the maintenance cost for 4 years. So it's about 1.4 crore on an average. It's on public domain. The second question, that sensors, the actual sensor only costs from $50 to about $200. Okay, but when you integrate it into a unit, there are 3 or 4 more components. That could go somewhere from $1,000 to about $3,000.
Why can't we make it in India?
So the most of these, the sensor units are now indigenously integrated in India. Even the gas sensors are most of the things, because see, sensor is a tiny part of the unit. Gas sensors are becoming fabricated in India. Particulate matter sensor cannot be integrated until now because our semiconductor overall, the the infrastructure was not at that place. But now I think that is coming within a year. But under this center, we are planning to integrate as a part of also National Center for Flexible Electronics.